Hello everyone. I hope you all are okay. So today, so I'll wait for some time for others to join. Meanwhile, I also check the previous week's query and all. Also, I think I haven't uploaded the lecture notes for you, so I think I will upload this after this session or the next session. As of now, don't see any. What are those? Okay, so there is a question from vs15 @gmail.com. So he asked that he has a question about some video. So YouTube video. Okay.
One other important feature of the SWIME portal is this Ask a Question tab that you have here. This is a very important way and process through which you can actually.
Okay. I think it will be better if I open this for you to. Wait. Okay. Link. Okay. Let me share my screen for you. I hope my screen is visible. So BS15 have raised a query. Yes, BS159025. I don't know what his name is. Some student. So his question is about what is happening in this video at 3 seconds. The piece of fluid and plasma Honorary book is not available. Please share book PDF. Thanking you. Okay, first let's see his question is about the video. Professor Pratap Haridos. So this is from Professor Pratap Haridos. He's the coordinator of NPTEL courses. So
One other important feature.
So what is the 3 second? I don't know what he meant.
One other important feature of the Swine portal is this Ask a Question tab that you have here. This is a very important way and process through which you can actually communicate your queries to the faculty and teaching assistant team that is offering the course to you. So you should make full use of this because this is the way in which you connect directly to the faculty from the or other leading institutes who are offering these courses to you. So supposing you click on this Ask a Question, uh, you will see something called a discussion forum open up for you. And then anything that you can post questions here. You can type questions here. You can see questions posted by other students at this particular forum. You can also answer those questions. So there is no restriction that only the professor should answer the question. As you can see here on top, it says it is a discussion forum. So you can discuss various points that you have with other students who are enrolled to the course. Please remember, this is a very nice opportunity. It's as good as discussing with your friends in your class. So you can do that here. The general etiquette that is required for participating in anything online should be followed. So no abusive language, no snide remarks, and so on. Stick to formal usage. You can use your own native language also to ask a question. Then presumably somebody else who knows that language can answer that question for you. So that is the kind of process with which you can participate here. The faculty who teach the course, as well as the teaching assistants who assist the faculty, monitor this.
So this is the video from the coordinator of NPTEL. So he basically discussed what the discussion forum is for. So definitely, as he suggested, you should make use of it for your queries and questions related to the course. And you can also ask your queries in your native language, whether it is Kannada, Malayali, Bengali, Hindi, I mean, whatever language you want, you can ask in that language too. There shouldn't be any barrier. Just don't think that you shouldn't post the assignment answers, and also should not ask the questions, assignment questions. So don't do that, because for your learning it is useful to do the assignments by yourself and then figure out. And that is what my sessions are for, right? So, and the next query, that to the physics of fluid and plasma. Yeah, this is a very good book. Obviously, this is a very standard and must-read book by Professor Anna Brai Chaudhary. So I also followed this book, and the physics of fluid and plasma. So I think so. I can't share you directly this book because I mean, if you are in some institute, so uh, just go through your library. Go to library. I think you will find this book. And if you online, I don't know what the subscription method is for. You can buy this book or ebook. So let me try also for you if it is available directly in online. So on the right Chaudhary. So this is one of the preview. Yeah, so it is available on Amazon and Cambridge University Press. And so I think you know how to download a book from Google. I can't disclose, or if any of your friend or your professor in institute available, this book is available. You can ask him to share, or I don't know. I have the book, but I don't know whether I can share it to you. Or I can do one more thing. If you still don't find that book, so I'll add this book to the drive list, and I will share the link with the lecture notes. So I will add that book there. So I think that will help if you don't find it. I will add the book there. So please follow the videos, and because sometimes you miss the video, I skip the video for some other time. So you can anyway uh, get the recording. So please go through the recordings. So since from past week I couldn't do the session because of some personal issue. So now I am back, so you can ask questions here. Thank you for understanding. So the next question is from Spondon Physics. What is happening in this video at 15 minutes 24 seconds? As for the lectures explains here, stress is caused by tangential force upon a unit area. Normal stress is the normal force upon a unit area. Can the shear stress be also accounted if a force is applied at some angle to a unit area? If not, then what kind of stress it is? So for this, okay, so Professor Subramania already answered this question. This one, but maybe had a force applied at any angle can be deformed into normal tangential component at the least. Okay, yeah, obviously he clearly answered this question. But if you want another explanations, I will give you one. So you know the how the stress is basically pressure, right? So the same dimension and kind of act same like it. So and shear stress. So I think I have explained what shear stress is by using the example of matchbox. So any force, so when it is applied in this direction, we consider that. But even if we apply the force along like some direction, some angle, okay. So you know the vector calculus. So basically you can decompose that force into uh, normal and tangential component, right? And then tangential component, that will be basically if this angle is theta, so tangential component basically f sine theta. So then we will consider the f sine theta to be acted for the shear stress. Okay. Sorry. So, so this is also answered by Professor Prasad Subramanian. And okay, this is already answered.
The number of particles in some representative macroscopic volume is much, much greater than one. So here is the other fuzzy thing in this definition. What exactly do you mean by much, much greater than? Yeah, are you talking about 10? Are you talking about 100? Are you talking about a million? Turns out, again, the answer is a little fuzzy. Ideally, you would have you would like to have as many particles as possible in a so that when you are reasonably far enough from it, you're not able to discern the dynamics of each particle per se, but you're able to discern the dynamics of the collective ensemble. Yeah, you're able to say, for instance, if I make a statement saying the number density of particles or the number density of molecules in the room is so much, well, you're mentioning the word density, which means that implicit in this statement is the fact that there are many molecules. Yeah, only then the concept of density makes sense. Exactly how many? Are there more than 10 molecules? In which case, do there have to be more than a million molecules? Well, that in fact depends. And again, in astrophysics, astrophysicists like to slide on thin ice. And there are situations where the number density is very, very small. Outer space, contrary to what's commonly stated, is not vacuum. It's there is matter out there. It's just that the matter is extremely tenuous, extremely thin, and yet one resorts to continuum description of the matter. And so many times, the continuum limit becomes a little questionable in astrophysical applications. Be that as it may, we'll come to it when we deal with it. But in everyday situations, such as the flow of air or something like this, the continuum description is very much valid in the following sense: the number of particles in some macroscopic, some representative macroscopic volume is typically much larger than one, because of which it's meaningful to talk in terms of to invoke macroscopic properties such as number density, pressure, and so on and so forth to characterize a continuum. So to expand on that just a little bit, here is an example of bulk properties from the microscopic kinetics. Yeah. So here's one example. Consider a gas whose molecules are in thermodynamic equilibrium, in that you can ascribe a definite temperature to it. The molecules have been bouncing around each other for a long time and have established an equilibrium amongst each other. And a consequence of this is that the molecules have a very definite distribution, F. By distribution, I mean, say, the Maxwell-Boltzmann distribution. So on the x-axis, say you might have speeds.
Okay, I hope that is clear. So, hmm, I think I also explained about this point. So, here the number in it must greater than one. Also includes the number density and the length scale of the suppose so the particles in a box. So length scale of the box. Yeah, so it shouldn't be comparable with one, right? It should be much greater than one. So yeah, as Professor Subramanian said, it is not very much precise. So yeah, but obviously it can't be just 1 or 10, right? So density also matters. I hope that answers your question. Hmm. So this is one thing. Okay. So then the next thing is about, yeah. So yeah, this is a little behind. Last time I explained the lecture notes for you. What do you mean by circulation and all? So yeah, and how you can reach to Kelvin's vorticity theorem. So I think I have explained this to you. I will share these PDFs, the lecture notes with you. Please carefully look through for these terms like implicit. What do you mean by implicit, incompressible, and barotropic, and also conservation? I hope, yeah, I think you already know. Still carefully go through this because this different theorem, Kelvin's theorem, Botticelli theorem, where you may come across another theorem. So there it is very much important to understand these terms. So this calculation have already been done for you. So I think you understand the Magnus effect. I cricket balls deep when it's find, yeah. This Magnus effect we also explained for the dipping of the cricket ball. So when bowler balls, the balls dip. Here the circulation is not zero, right? So there is circulation or dipping. You can see. Set up circulation. Spin ball inside fluid. Inside fluid. Spin ball. Yeah. So denser stimuli means faster flows. Then E below is greater than E above and P below less than E above. Yeah, for viscous flows, these forces are being measured. So we already go through this force balancing. So yeah, remember this term we use this. So viscous stress this zeta is equal to mu du dy. Right. And then mu del square u is grade of P. Force on fluid partial. This Euler equation plus viscous terms give rise to the Navier-Stokes equation. Let us explain this. Traceless. Yeah, this I've already explained. So then and rectangle. And why the b will be minus 2 by 3a? Think that I'm going to explain to. Why not find isotropic viscosity? Please ask questions on the forum if you don't understand any part of it. Otherwise, we will move ahead. Particular solutions to the Navier-Stokes equation reflect boundary condition. So u is ux, y, and other are 0 and 0, and p is equal to qx. And then so u is like this, ux. This that depends on the y, function of y. Thin pipe, ignore body, gravitational forces, assume static flow. P is equal to kx, right? In a row, the equation this Navier-Stokes equation, what it is? Navier-Stokes equation. Here, Navier-Stokes equation rho del u del t plus rho times u dot grad of u equal to minus grad of p plus mu del square of u plus rho times g in Eulerian frame. Okay, so then by making this equation, making use of this equation, as it is a steady flow, so del u del t will be 0. Okay, so this term vanishes, and if you don't consider any body force, then g is also 0. So we remain with these terms. So for given u dot grad of u, so u is only ux, right? So this is ux del x of u. Other terms will be 0. And del square u will be, so yeah, you can't, I mean, you can get this by indirectly. So curl of u is basically this, right? Uh, minus, so this is the vector formula for curl. Minus curl of u plus grad of del dot u. So curl of u will be, so curl of u will be basically 0 because there is no rotation. Okay. This is a rotational vector, so curl of u is 0. So basically this term vanishes. Second. So yeah, so this term will be 0. and then Okay, so and then del dot u will be simply del ux, and this is uh, del dot u, right? So del, wait a minute. Okay. Okay, so then, so we read through this point. So from here, we'll get that. So del x of u, del u del x will be 0 as u is a function of y, right? So from here we'll get, because as u is a function of y, so we'll get only q del y2. So this term 0, then obviously then grad p will be simply mu del square u. Right? So mu and del square u is this, and grad p. So grad p is del s I hat. So equating both sides, you will get this. And if you equate this to minus k, then ux will be simply, wait a minute, there is a k by mu will go this side, and then we'll get uh, from the first integration we'll get ky plus uh, some function of b as a of y, and then after second integration it will be by, and it will be minus ky square by 2. So ux will be a plus by, something like that. And from the boundary condition at ux 0 is 0 at y equal to 0, so a will be 0, and ux of a will be p is equal to kx. uh, yeah, because p is kx, so del x is equal to k. So this is a minus some. Okay, anyway, rotation is not. So ux a will be 0. Yeah, this is the thin pipe, so upper limit velocity is 0 there. So b will be plus k by 2. So we'll get plus minus, not a, yeah, plus minus k by 2. So x will be k by 2y minus k square by 2. So this is just an equation of parabola. Okay, this is equation of parabola where x is equal to uh, not x, or yeah, or x is equal to It's not y square is equal to 4x. Or ay square plus by plus c is equal to 0. Okay. So that means the parabola will be on the negative side because of this sign, and it is along this. Y square is 4x. No. This is along x. X is equal to, basically you can find x is equal to ay plus b square plus c, or so it will be on this. So yeah, this is the velocity, viscosity and microscopics. v0 y plus dy lambda yz 0. Particles from slower stream at y move upwards to join faster streams at y plus dy, carrying momentum with them. Drag felt as an effect of intermolecular collisions. Yeah. So basically particle, here the particles has lower speed. U0 particle has lower speed, here the particle is at a higher speed. Suppose a scenario like this, then the lower speed particle will move upwards to join the faster stream. They will carry momentum with them. Then the drag will happen. So suppose the fluid is moving, and this is slow fluid, fast fluid. So obviously the fast fluid will carry the slow fluid along with it. So it seems like the slow fluid go upwards and join them. Density flux from y to y plus dy. Effect of intermolecular collisions. Density flux from y to y plus dy. Oh, yeah, change of velocity in traveling mean free path du dy lambda. The velocity change. The length is scale cancels, but this is the scale of velocity. So this is basically velocity gradient. So for length lambda, for length lambda, it will be du dy times lambda. So the momentum carried is a change of velocity. Change of velocity times momentum carried from layer at y to layer at y plus dy to layer at y plus dy area per unit time will be two times because this collide and then again come. So the whole momentum carried will be twice of that. So rho b RMS of du lambda, the density flux. This is basically mu du. This is rho b RMS lambda is mu. Okay, so that's all. Then we'll head to the sample assignment problem. So I hope you understand how. This is just to explain the 2 lambda rho b RMS is basically the mu. Yeah. The mu basically what is called resultant mass or effective mass. So I'll give you some time. Settle down here. So now we'll start our assignment problem solution session. So the first question, consider a fluid or for which both the potential phi and stream function psi satisfy the Laplacian del square phi is equal to 0 and del square psi is equal to 0. Which of the following statements are correct? Did we discuss this? Okay, anyway, del dot u 0, the fluid is incompressible. Del dot psi is 0, the fluid will not stick to the solid surface. Okay, so you have given this, consider, you have just given this, it's called this Poisson equations, where just rho is 0. So yeah, so the correct answer will be, yeah.
It's 2 o'clock.
For such a system which obeys the potential stream function Laplacian 0, the fluid has to be inviscid. That means okay. Inviscid means the fluid will not stick to a solid surface. There will be no viscosity. Incompressible, so B is wrong. And irrotational means, yeah, del dot psi is 0. The only condition that does not match is option B. Yeah, I hope that is clear to you. Assignment question number 2 is a horizontal jet of fluid is spread on a square plate of side 2 meter. The density of the fluid is 100 kg per meter cube and the speed of the fluid when it hits the plate is 5 meter per second. The force needed to hold the plate stationary is, you have to calculate the force. So the horizontal jet of fluid, so the fluid is horizontal. Okay, so there will be no gravity force. Square plate length is given, dimension is given 2 meter, density is also given, and speed when it hits is also given. So obviously you will use the, you will make use of the Bernoulli's theorem, that it will be constant and there is no body force, so T is 0. So P plus half rho B square should be constant. So yeah, so when it hits the plate, the V is 5 meter, right? Rho is given. So you will calculate rho V square, half rho B square, and at spread on a square plate. Yeah. And the plate dimension is given 2 meters. So area is 4 meter, right? Should I calculate this? The force. So you have to calculate the pressure. You have to calculate the pressure. So then rho V square will be 25, 2500. 2500, 2500 by 2. Okay, that is 2500 by 2 is 1250. Right, 1250. And at that time, is uh, so P will be equal to half rho V square because initial point P is 0. So only P remains, and at the end, yeah, P should be 0. So the force needed, so P is equal to half rho V square. So P will be 1250. And well, dimension 2 meters, so area is 4. 1250 times 4 is 5000. So the right answer is 5000 Newton. Right answer will be C. Okay, so this is the Bernoulli's theorem, typically Bernoulli's theorem exercise. So then question number 3, choose the correct statement. Viscosity will produce circulation in fluids. Kelvin vorticity theorem is only true for inviscid fluids. Bernoulli's theorem is not applicable if curl of U is not equal to 0. E square by 2 plus integration of dp by rho plus phi is equal to constant of fluid flow where energy dissipated throughout the flow. So I'm not interacting because there is no one to interact right now. So I'll just give you how to solve this question. So you can spend a minute here, understand how to solve this. We already described the circulation, right? Okay, the integration of q dot dl, or if you apply Stokes theorem, it will be integral of omega dot dA because curl of u is omega. And there is Kelvin's vorticity theorem. I told you initially that you should be careful to fathom these quotations, these conditions, viscosity, compressibility, and barotrophicity of fluids. So I think you understand that B is correct. Bernoulli's theorem, when applicable, think about it. Okay, I'll give you the answer and then maybe you can think. So yeah, viscosity produce circulation because I told you that density streamline means larger velocity. So at the bottom, the velocity is more than the upper side. So that basically gives rise to the viscosity, right? And that makes the speed ball dips. The option is correct because it creates vortices in fluids due to velocity gradients. Yeah, the same thing. Kelvin's vorticity theorem holds only in an invisible fluid. Bernoulli's theorem is applicable along a streamline regardless of omega. So yeah, Bernoulli's theorem is along the streamline psi, the stream function psi is applicable on the streamline, and it doesn't depend on the omega. Curl is omega, right? So either omega is 0 or not. Finally, the energy consumption along a streamline is not possible for a dissipative system because yeah, this constant should only be for conservative system, right? For a dissipative system. Moving on to the next sample question. When the term mu del square u is present in the momentum equation, it means that the fluid described by this equation will stick to the surface of a solid body imagine it. The fluid described by the equation will not stick to the surface of a solid body imagine it. The fluid is rotational, like a small paddle wheel placed in interior of the fluid flow will not rotate. The fluid is rotational. I ideast, that means that a small paddle wheel placed in the interior of the fluid flow will rotate. So yeah, so what does this term signify? Should understand. I told you when it comes to the Navier-Stokes theorem, these terms come. So option A, the fluid described the equation will stick to the surface of solid body. The fluid is viscous, right? So obviously the upper surface fluid will stick to the solid body. And a viscous fluid is rotational. Yeah. So C is it incorrect and option B is incorrect. That basically B is opposite to the A and C opposite to the D. So moving on to the next question, sample assignment problem, question number 5. Consider an inviscid monatomic ideal gas of 1 mole. The specific enthalpy per unit mass of the gas will be, I think, come across the term enthalpy, right? So basically the energy released, the enthalpy of the system So yeah, so this is a monatomic fluid. That means the gamma will be 5/3 as the degree of freedom is 3, and we know that gamma is equal to 1 plus 2 divided by f. So that basically 5/3. So then what will be the enthalpy? Right? Enthalpy as E plus V is per unit mass. So I'll yeah. I think I haven't put the answer code here. Anyway, doesn't matter. Did I put here? Anyway, even if you don't have, think you can answer this. Let me check. It is not given. Anyway, enthalpy is E plus V. So U will be monatomic means gamma is 5/3. So it is per unit mass. That's why it will come by rho. Is 2 by gamma, right? So 2 times 2. So energy is 1 by gamma, P by gamma. So that is basically 3P by 5 rho. So moving on to the next question. The now time for the assignment question where you will come close. Okay, so I think yeah. So how we calculate the energy? We know that uh, so energy is from the pressure 3/2, right? 3/2 kT. E is 3/2 kT, or for on mole 3/2 nkt, and P is equal to nkt. So E is equal to 3/2 times P. So P is 3/2 times P, and uh, yeah, gamma P. So gamma times, and for 3/2 times gamma. So gamma is 5/3, 3 cancel out. So that basically will be option D. Yeah, 5/2 P by rho is the enthalpy. Then We move on to the assignment question. Previous, so anyway. Consider a small sphere immersed in a fluid that is steadily flowing past it in the exact direction at a speed u. As per an observer standing in the lab, there are no temporal changes in the flow, i.e. del t tends to 0. Select the statements that are correct. If the flow is perfectly inviscid, the tangential and normal components of fluid velocity at the surface of the sphere are 0. If the flow is viscous, the tangential and normal components of fluid velocity at the surface of the sphere are 0. If the flow is perfectly inviscid, the fluid velocity u can be expressed in terms of the gradient of scalar potential phi, i.e. is equal to minus grad of phi. If the flow is viscous and incompressible, the fluid velocity u can be related to the Laplace equation involving the velocity potential. I think I read out the options you can anyway. So it is talking about a smooth sphere and velocity is only along x-y direction. This video. So which is not correct. So the flow is inviscid, the viscous term in the Navier-Stokes equation is absent. And the boundary equation only contains first derivatives of the fluid velocity, right? So therefore only one boundary condition is required on the surface of the sphere. Therefore, conversely for viscous flow you need two boundary conditions. And for inviscid flow you only need one boundary condition because viscous term is absent. And the velocity equation only contains first derivative, so only one constant or one boundary condition. And the most commonly boundary condition requires this fluid to stick on the surface of the sphere, both normal and tangential components and 0. Okay, so option B is correct. If the fluid is inviscid, it's a rotational, at east curl of u is 0, and then you can define u as 1 is equal to 5. For a viscous flow, this is not valid. Condition incompressibility is not relevant. For a viscous fluid can be incompressible, but doesn't matter. So right answer option B and C. Okay. I think I solved the questions. Anyway, the number doesn't matter. Consider two Earth-like planets 1 and 2. Both the planets have isothermal hydrostatic atmospheres. The atmospheric temperatures on the two planets are T1 and T2 respectively. Both the planetary atmospheres are under the influence of a constant gravitational acceleration g. You can assume that both the atmospheres comprise of fully ionized hydrogen. One proton and one electron. In atmosphere 1, let the length scale over which density changes by a factor of E be L1. The same quantity for atmosphere 2 is L2. Pick the correct statements. In both cases, the density will decrease with height from the surface. L1 by L2 is equal to T by T1. Which we are talking about two Earth-like planets. That was the temperature given. Atmosphere are under the influence of gravitational acceleration. Length scales are given. So you know the pressure gradient. Grad P and dp teacher is minus rho g. Basically, P is rho g h, right? From that equation, and P is mu kt, and mu is sorry P is nkt, and n is rho by mp. P is rho kt by mp. So dp so replace this. So we'll get we'll get KT by MP. We'll go this side and there will be 1 by rho d rho dz. Right? So basically d rho by rho and there will be dz. So rho is ln. So but inversely, so L1 by L2 is equal to T1 by T2. Right? Temperature and both are in the denominator. Yeah. So option D is correct. In both cases, the density will decrease with the height from the surface. Hmm. So yeah. Consider a circular pipe of diameter 2A filled with a viscous fluid. The axis of the pipe is oriented along the horizontal x direction. Consider cylindrical coordinates so that r is equal to 0 and the axis of the pipe and r is equal to 8 and itself. The uniform pressure gradient along the x direction applied to the fluid with the statement which is correct. Fluid will accelerate in the x direction. The fluid will flow with an x directed velocity given by xr, x3 minus r square k square. The fluid will flow x directed velocity given by xr. The quantity dvx or dvr is not equal to 0. So this is a viscous fluid, right? So the pressure gradient force will be balanced by the viscous frictional force. Second force will be balanced by the viscous frictional force. So the pressure gradient force is frictional force, yeah. There will be no net force on a fluid parcel, and statement A is clearly not correct. Fluid don't accelerate. The fluid will flow in a, both statement B and C look right in that the fluid velocity is maximum at the center and decreases towards the pipe. Also, however, the boundary condition mandate that the fluid sticks at the boundary, the fluid velocity goes to 0 at the walls. Option C agrees, right? Mandate that the fluid should stick the boundary goes to 0 when R is equal to A. But when it is R is equal to A, it doesn't guarantee. Option C agrees with this. Statement is clearly right for a viscous fluid, right? So option C and D are correct. Consider a smooth spherical ball of radius A falling through an infinite viscous medium under the influence of gravity. Intuition tells you that it will stop accelerating after some time and will attain a state terminal velocity. By conducting experiments on balls with various radii, we observe that the terminal velocity is proportional to A square. All the balls are made of the same material, the density are the same, which is correct. So we know F is equal to 6 pi V eta, right? And V is proportional to A square. A proportional to A cube. The drag force on the ball is proportional to A. On the ball proportional to A square. The velocity is attained because the drag force is equal to the gravitational force on the ball. So obviously this is the case, right? Option D is. This is the case that obviously it will attain because it balances. Sorry, I forgot to put option D there. The drag force on the ball is proportional to A proportional to the square of its velocity. Yeah, because F is equal to 6 pi VR. So proportional to A. Velocity is reached when there is no force on the ball. Drag force is gravitational force. Fg proportional to mg, that means m is equal to rho a cube, right? Because this is spherical. So there will be fourth third pi partition proportionality. So let f be proportional to a to the power p times u to the power q. So just the dimension analysis. So we need a p u q proportional to eq. We also know that u proportional to a square. U proportional to a square. So there will be p plus 2q. So p plus 2q equal to 3. So of the choices given above, so only when p and q is on, this satisfied. So option D. And drag force on the ball is proportional to all A and proportional to its velocity. And so it's option A and C. There are only another question given. Consider an incompressible fluid flowing through a pipe. The pipe is horizontal, but its cross-sectional radius is not constant throughout its length. In section 1 of the pipe, its radius is 2 cm and the flow speed is 10 cm per second. In section 2 of the pipe, its radius is 5 cm. Sections 1 and 2 are joined smoothly. There is no abrupt transition to the currents. The fluid velocity in section 1 greater than 2. Pressure in on greater than pressure in 2. Velocity in on less than velocity in 2. Pressure in on less than pressure in 2. So from mass conservation, because it's the incompressible fluid, so mass conservation we know that A on B on is A2 V2. So pipe section 1 pipe radius is 2. Okay. So A is 4. Sorry, pi r square. Anyway, so pi cancel out. So beyond rho r1 square v2 r2 square. And speed is 10. So 4 times 10 40. Radius is 5. So 25. So 40 by 25. How much is that? 1.6. Right? Which is less than v1 because v1 is 10 centimeter per second. So v1 greater than v2. So option A. From Bernoulli constant P plus half rho B square, P1 plus half P plus half rho B square should be constant. So if P1 is more, so P1 should be less. So that is that pressure in on is less than pressure in 2. Yeah. So these are again from basic the Bernoulli equations and the viscosity and the mass conservation relations. I will share this. Here's the diagram that the from the ball that this is the R, right, and this is the gradient, pressure gradient. Cylinder with viscous fluid flowing in x direction with a horizontal motion. And with the terminal velocity always attend because the drag force is equal and opposite to the gravitational force. That's the case here. Because when a ball is coming under the pull of gravity of Earth, it will accelerate. Only one case where it won't accelerate when it will be applied by an equal and opposite force along it. So then it will just attain the constant speed that is called terminal velocity. I think you will also come across this in class 11, where you know the drag force is 6 by VR eta. We can't process with it because then you have to the expression of eta. So this is better to do this by dimensional analysis. And that's all for now. The next time we will start the next assignment question and solution, and I'll move a little fast the next time. Can't go slow. So for now, good night. Thank you. Take care of your health and see you next time. Bye bye. So yeah. Okay. So I'm stopping the recording. Hmm.